Hello, my name is Kristen Deason, and I am giving a presentation on EPA's methods for evaluating wetland condition, number 20 on wetland hydrology. This module was actually published in 2008. So the module stated two general purposes of the document, and the first one was to describe and discuss the general hydrologic properties that make wetlands unique. And the second one was to provide an overview of the processes that control wetland hydrologic behavior. So as much as these two purposes look at generalities and an overview, this document was actually pretty detailed. It was 33 pages and actually included a lot of formulas. So my intent here in this presentation is to give you the conceptual background that the document presented. And if you need to know some formulas, you can cite the document and look into it more. So wetland hydrology is actually very important due to its position in the landscape. Wetlands exist between the terrestrial uplands and the aquatic environments such as lakes as depicted in this figure. The transition zone in between allows for shallow hydrology, whether it's at or near the surface. And this makes wetlands unique, where they can range from submergent wetlands, shrub wetlands, or forested wetlands. So the geomorphic position actually plays a very important role in forming wetlands, as they normally form in flat, shallow slopes where water is at or near the surface. This figure shows some examples. For example, we have a seepage slope wetland over here, what occurs at the bottom of a mountain or a hill. We have depressional wetlands that just form in areas that are a little bit lower on the landscape. We also have riverine type floodplain wetlands that occur due to overbank flooding. And then we also can have perched wetlands that form due to an impermeable soil substrate. So as you can see, the energy of water is a really big factor in forming these wetlands, where water wants to go from high energy to low energy, from high elevation to low elevation, or from high pressure to low pressure. So now that we know why wetland hydrology is unique, how do we measure it? The module presented three different ways to measure wetland hydrology. The first is to measure its water level, which is the general elevation of water relative to the soil surface. We can also measure the hydropattern, which is the timing, duration, and distribution of water levels. And finally, we can look at the residence time, which is the travel time of water as it moves through the wetland. As we know, the amount of water can significantly affect the soil oxygen concentration, which dictate what type of vegetation can grow or survive in these wetlands. Typically, in open water, deeper areas, we have more floating type vegetation. In shallower water, we have emergent plants, such as this marsh. And then oftentimes, if we have exposed saturated soil, it allows macrophytic or forested wetlands to persist. And as we know, even though wetlands have such low oxygen, they are actually some of the most biological productive ecosystems. And these plants have special adaptations to survive and prosper in these environments. So when we look at water levels, we need to understand that there are saturated and unsaturated soils. Saturated soils have low oxygen, which can cause anaerobic conditions to develop. And water levels actually serve as an indicator of dissolved oxygen in wetlands, which this figure on the left shows, where when we have wetter sites, there's higher water levels and low DO. Drier sites have low water levels and high DO. So this shows a transition from a saturated zone up to an unsaturated zone. And as you can see, in the saturated zone, we have a very low dissolved oxygen concentration. And as we move up to the unsaturated zone, the dissolved oxygen goes up to 8 milligrams per liter. This figure over here on the top right shows the difference between unsaturated soils, saturated soils, and flooded soils. So this is just to understand that not all wetlands have to be flooded. A lot of wetlands only have hydrology in the subsurface, which causes the water pores or the pore space to be filled with water. And finally, down in the bottom right, we show capillary rise, where your water level could be way down here in the subsurface. But depending on your soil type, whether you have a sand, clay, or loam, it can actually cause a saturation above the groundwater line, where clay, because of its high surface area, allows the capillary fringe to be way higher than the actual water level. So now that we know the importance of water levels, how do we monitor it? A simple, inexpensive way is to install a staff gauge. This picture on the left shows several staff gauges on a riverine system where you want to install all of these because if the river floods and the water levels rise, you may be only able to read these two closest to the upland. The picture on the right just shows someone reading a staff gauge, and this looks like it's in a wetland, so maybe they've only installed 2 staff gauges because the water levels don't fluctuate as much. Another way to monitor water levels is to look for water lines. I have 2 pictures here that I've taken. One of these on the right shows the water marks or water lines on these black gum trees. And this is an indication that this is where the water normally sits in this wetland, even though we observed it at a dry time. This other photo shows a box culvert at a stream crossing with some adjacent floodplain wetlands. I'm marking here the watermark that has been formed because the water level typically sits there. A disadvantage with this method is it doesn't give you a detailed look at the different water levels. It can only show you the normal water stage. Another way to monitor water levels is to install piezometers, which are basically wells that are dug into the ground and they have a fine mesh screen or some other type of screen on the bottom that only lets water in and it doesn't let other sedimentation or mud in. And what you can do is, like in this photo, you can drop a water level reader down the well. They have 2 different types. They have a weighted tape down here that you can put chalk in all over. And then they also have this one that is more of an audio or visual signal. So another way to monitor water levels is with automated piezometers, which are transducers that you can install on the ground that record pressure of overhead water. Here I am in the field, actually at one of our mitigation monitoring sites, and I'm just showing you one of our piezometers that we have installed in a PVC well, and dropping it in there, putting a cap on it, which does not allow rainfall to come in. Down here on the bottom, I show the different ways that you can actually set these piezometers for reading. And the advantages of using these automated transducers is that you can leave the site and have it be monitored for months at a time, years at a time, and only go back to check the data whenever you need to download it. However, if you are not there monitoring these piezometers, malfunctions can occur. These are electronic devices sitting in water, or wildlife can come knock them over, a tree can fall on them, anything. And actually here I am checking another set, and what happened here was that we had the device hooked up with wire that was rusting, and eventually it broke. And so what I was trying to do was retrieve this transducer because it had valuable data that we needed. And after this, we replaced all of our wells to have stainless steel type clamps that would not rust over time. So now that we've talked about water level, let's talk about hydropattern. So as we know, the hydropattern is the frequency and duration of saturation as well as the areal extent and timing of inundation. It includes the differences from inflows and outflows from the atmosphere, the groundwater, and surface water. And normal examples of this include salt marshes that fluctuate daily, bottom hardwoods that fluctuate more slowly over time, and other systems that are more static and don't really change in hydro pattern. So if we take water levels and hydro pattern, we can actually present them on a graph called a hydrograph that can help show changes. These changes could be interannual, they could be seasonal, you could identify individual events, or you could even see daily fluctuations in the water. So I pulled some example hydrographs on sites that I work on. These are all different wetland mitigation areas. And this particular one shows more of a depressional bowl type wetlands, where you can see that the hydrology is present from about November to April. It drops and then it picks up once again in the summer. And this can really be dependent on when you get your spring or summer rain. But these wetlands are used to dry summers. This is what we would call a more flashy hydrograph, and this is actually a floodplain wetland directly adjacent to a stream. So what you're seeing here are quick peaks and drops with the stream flow, and that could be from a stormwater event or potentially a release upstream, but the wetland is functioning consistent with the stream's hydrology. This one is a headwater wetland displayed in yellow, where it gets most of its hydrology from either groundwater or precipitation, and it doesn't vary all that much. And then finally, this is a beaver impounded area. So actually the blue line down here is our reference wetland. So that's what we are trying to meet. However, because the beavers had this dammed up, all of our data is up here above a couple inches, and it ranges all the way up to 30 inches. It actually goes off the graph here and here and here. So this was extremely elevated water levels due to the beaver impoundments. So this is another way to depict hydro pattern on different plots. The module instructed that you could use the hydro period plot to show the duration of flooding versus stage. You can use the one in the middle, wetland stage frequency plot, to show the number of exceedances per year, where the longest duration of flooding occurs at the lower stage and the shortest duration of flooding occurs at the higher stage. And then you have year one on the far right, which is the wetland stage frequency duration plot, and that shows the duration of flooding versus the stage for a few different frequencies. So the final hydrology factor the module went over was the residence time. And the residence time is the ratio of volume of water within the wetland to the rate of flow through the wetland. If you have a short residence time, that means that your flow is greater than your volume. So your water is leaving your wetland faster than you have volume. And if you have a long residence time, that means your flow is less than your volume. So if you have a long residence time, you actually have a large volume that is flowing slowly. So there are ways to estimate residence time, but it cannot be accurately used for wetlands where water mix, where there are multiple inflows and exchanges at different points within the wetland, and when the flow into the wetland is not constant over time. Residence time can be accurately estimated for a steady or constant flow where you have a first in, first out, you have a single location inflow and a single location outflow, and also where there's no atmospheric or groundwater exchanges, which is obviously not many wetlands. And so this is actually very hard to accurately estimate, but you can calculate it using an equation where it compares the volume of water within the wetland to the flow rate, or you can actually use tracers that you can add at an inflow point and monitor where they come out. So we just went over the three important factors of wetland hydrology, which is the water level, the hydro pattern, and the residence time. All three of these are influenced by hydrologic inflows and outflows, which makes up the water budget. So water budget inputs come from precipitation, overland flow, surface water, overbank flow, groundwater, And you can have outputs from wetlands, whether it be from surface water outflows, evapotranspiration, groundwater recharge. But keep in mind, all inputs and outputs should be expressed as a volume or depth per unit time. So there's a lot going on under the ground in wetlands, and we call that the subsurface. And when you're thinking about water storage in the subsurface, you think about specific yield. And the specific yield is driven by mineral or organic materials and whether they release less or more water due to their porosity and ability to retain water. So this graph over here shows that specific yield for silt and clay is pretty low because that clay has a high surface area and holds on to that water. But when you get up here into coarse sand, you have a high specific yield. And then it goes back down for coarse gravel. If you know the specific yield, you can actually generate these graphs called the stage area and stage volume relationships. And these graphs can be used to predict what changes in stage will do to the changes in volume. So one thing, a take home here, is to notice the sharp change once water level falls below ground and when water levels top the natural bank or levee. So as we just discussed, it can be difficult to quantify and assess subsurface water. However, if you're looking at above ground water, you can determine its area or volume in a couple of different ways. You can use topographic maps, you can use surface maps, you can use aerial photography taken at different water stages. And I have an example of this over here on the right. This is actually near a boat ramp I use quite often north of Augusta where the Savannah River is dammed up. And the photo in the top, so here's the boat ramp right here, shows a lot of exposed soil along these banks and a low water level where this year they actually could not even access the boat ramp. The photo down here obviously has water inundated much higher. So you can take aerial images like this and estimate the area, and that can give you a factor to use in determining the volume. You can also use a tracer, but tracers have to be mixed thoroughly and you have to measure the concentration. And two examples of using tracers, you can quantify whether evapotranspiration is only outflow and no inflow. Then the tracer concentration will increase over time as the volume of water within the wetland decreases. Another example is when precipitation occurs but no outflows, and the tracer concentration will decrease over time. So now that we've looked at subsurface water, surface water, we can look at the water budget as a whole. And there are four general sources and sinks in wetlands. We have atmospheric from rainfall, snow, evaporation, transpiration. We have subsurface inflows and outflows. We have surface water, and we have marine system, which is the tidal variation. Any of these water budget components are very complex, especially when the inflows and outflows are from different sources and sinks. So this triangle image on the right-hand side just shows how different water budget components, such as surface water, atmospheric exchange, or subsurface exchange, can drive what type of wetlands form. For example, when we have a lot of surface water exchange, that is typically a riverine or fringe wetland where you're getting that overbank flooding. And then, of course, there are a lot of different atmospheric sources of water, such as rain, snow, hail, sleet, freezing rain, fog, dew, and frost. So when you're looking at atmospheric exchanges in the wetland water budget, rainfall plays a big role. However, rainfall can be discrete, and it can differ in intensity, duration, frequency, and areal extent. Some areas might get a ton of rain from an isolated thunderstorm. A town right next to it maybe will get none from that same event. So it's very important that you consider using on-site rain gauges, and that's typically the preference. But if you were to use regional data, take that with a grain of salt and use it for estimates only. So another atmospheric exchange to consider in the wetland water budget is evaporation and transpiration. Evaporation dominates where there are open water systems and vegetation is not there. Converse to that is where transpiration dominates in systems where large coverage of vegetation exists. And finally, evapotranspiration in general is affected by a lot of different things, including leaf or stem area, the air or water or plant temperatures, the atmospheric humidity, the wind speed, and the water potential of exposed soils. So it is possible to monitor and measure these atmospheric exchanges. If you're interested in monitoring rainfall, you may install a rain gauge on your site. They're typically inexpensive and reliable. Oftentimes, one rain gauge is sufficient for wetlands of a reasonable size, but multiple rain gauges might be needed for larger wetlands. They have manual rain gauges or automated ones that record the rain levels over time. You can also measure the evaporation with an evaporation pan, and those can also be manual or recorded, but keep in mind they can be affected by local conditions such as shading or wind. Down on the bottom, I actually just have a graph I pulled from a paper that shows precipitation versus evaporation and how important it could be in the wetland water budget, especially considering seasonality. So here we have in the months of February through June where there's more precipitation occurring, and then throughout the rest of the year, there's more evaporation occurring. So the next section of the module focused on measuring subsurface and surface water. So first, we need to understand the different outflows or inflows from subsurface. So when you have outflows, that's actually a groundwater recharge, where there is a downward lateral flow from the wetlands to the underlying aquifer. And if you have a groundwater discharge, that is actually a subsurface inflow, where shallow topography allows drainage from nearby uplands or wetlands to filter to the wetland. The module went into how to measure and predict groundwater gradients, which is basically the energy force that causes groundwater to move. It specifically talked about the change in head or pressure, which is called the hydraulic gradient, and you can estimate that in a three-dimensional way with the X, Y, and Z, or just a two-dimensional way with the X and Y to represent the horizontal and vertical flow. And that's what I have depicted over here on the right-hand side is the horizontal flow, as well as the delta H, which represents the vertical change in height. And this can estimate the change in water levels over a distance. The module also briefly went over Darcy's law and groundwater flux, where hydraulic gradient and hydraulic conductivity are combined to determine the groundwater flux, or the rate of volume of flow. In general, flow is from regions of higher hydraulic head to lower hydraulic head, and you can estimate this at any one point. Once you have that estimated flow at one point, it can be multiplied by the cross-sectional area of the unit in question to estimate the total flow across an area. This is depicted on the right, which shows that you can measure it for a gradual gradient, a steep gradient. You can look at it in different types of soil material, whether it be coarse or fine sand. You can also look at it in a different cross-sectional area. This has a larger area than this one, and this Darcy's law groundwater flux equations help you estimate all this. You can monitor subsurface flows by installing different piezometers across a wetland. Keep in mind that groundwater gradients and flows have great spatial and temporal variability. So if you want to accurately determine the flow, you will need a high resolution of sampling that is required both spatially and temporally. You need horizontal and vertical measurements at frequent time intervals, and you also need many piezometers at different depths and distances away from the wetland as shown here. Estimating flow requires a known hydraulic conductivity, which can be estimated by using core samples, using aquifer tests, or just using a standard table of values. Keep in mind you need to know both the hydraulic conductivity and gradient to calculate this subsurface flow. Now we'll move on to surface water exchanges. On the left-hand side, I show stream flow and the difference between base flow and storm flow. The base flow is the orange line down here, which is your standard rate of flow in a stream. The storm flow is a high peak after a rainfall event. And the picture on the right shows what can happen during these storm events when you don't have wetlands. So in the top, we have all these different wetlands adjacent to the stream, and we have a very gradual peak every so often. When you remove these wetlands from the stream, you have huge rises and falls in this hydrograph now. So knowing that, it is very important to know or predict the open channel surface flows, such as in streams or rivers. The image over here on the right-hand side shows how you can measure this. And in a stream, you usually want to subdivide the profile out because the width and the depth vary so greatly, which affects the velocity at every single one of these subsections. You can total that all up to get your total discharge for the entire stream. And you want to try to do this in an area of the stream that is uniform and avoid areas that could have backwater effects from downstream inflows. Another way to measure these surface flows is with control structures. There are different flumes and weirs that allow for velocity to be calculated. The difference would be in a flume, like the one over here, there is no upstream stilling basin, which allows sediment to pass through. And over here we have a weir that has the settling basin up here. But the weir shape can be a lot of different varieties. They have triangle, V, square, and then we have our standard culvert that you can just measure flow in. Here's a guy standing in the middle of a box culvert. Another way to estimate surface flow is using the Manning's equation. However, this should only be used when control structures are not present where you can get measurements or when actual in-stream measurements are not possible. And the Manning's equation uses the Manning's roughness coefficient, which is the term N, which can be found in pre-existing tables, but it's based on the stream's substrate material, and that being vegetation, shape, or sinuosity. And the roughness coefficient dictates how easily the water moves through. If you have a lot of obstructions, the roughness coefficient would be reflective of that. So the Manning's equation uses hydraulic radius, which is based on the cross-sectional area, as well as the wetted perimeter. The module went over two other types of surface water flow, that being overbank flow in wetlands adjacent to riverine systems. As you can see here, this bridge is completely inundated in this floodplain wetland. And also according to tidal exchanges, where the ebb and flow of water due to ocean tides, where at low tide you might have no surface water, and at high tide you might be full of water. The module went over how to calculate the harmonic wave height with certain equations. Keep in mind that it's not suitable for all coastal areas, but it considers the most important factors that affect water energy in a tidal system, that being time, distance from the wave to the shoreline, the wave frequency, the wave height, the hydraulic resistance, where there is a dampening coefficient that accounts for the dissipation of energy as it moves across the landscape, and then the hydraulic diffusion. In general, low frequency waves such as daily or semi-daily are attenuated less, lag more, and propagate deeper into the coast. Of course, tides can affect wetlands far away from any saline sources. The module wanted to point out to always consider other impacts to tidal system, including impacts from fresh water. When you put large freshwater inputs into a salt marsh, it can affect the salinity, the temperature, the DO, and the sediment concentration. However, sometimes this can be beneficial. For example, in the Mississippi Delta, historically freshwater was deposited and created these coastal marshes. A detrimental example is when freshwater discharge or urban wastewater or stormwater is discharged into the marsh. So now that we know all this about estimating wetland hydrology, the subsurface, the surface, we also want to consider that there can be many different alterations to such hydrology, some of which are natural. So one really important rivers that form floodplain wetlands. And I have a video here of a site I go to often where the stream is very far away from where I'm standing. But this is all overbank floodplain water that is literally rushing through this forested system. And that obviously has a very big impact of forming these floodplain wetlands. Other effects that can alter hydrology is glacial scour, tectonic uplift, dissolving of carbonate aquifers, erosion, when peat-filled depressions fill in where they were originally formed, and then also beavers. Over here, I have a picture of two of my coworkers. The one in the orange is standing on top of a beaver dam. The one in the green is several feet lower than him. And we actually pulled that dam by hand and released all this water. And you can see just the massive impact this would have on a wetland. So all this is just to show that wetlands are constantly being formed, they're being lost, they're being changed, and it really depends on the forcing functions that are acting upon it, all of which can change the hydrology. Not only are there natural alterations to wetland hydrology, but of course humans have induced some changes as well. There's a whole list of common human alterations. We increase sediment production, we increase surface water inflows, we create reservoirs, canals, levees, dikes, we dig ditches, we dig channels, we pump groundwater, we irrigate areas that can actually make wetlands wetter, we trap beavers that can reduce wetland formation. One that I have depicted over here is actually building of obstructions or roads. And this road right here called Enclave Way, before this subdivision was developed, this whole system was a forested wetland. After this road was developed, to get over to this subdivision, you can see the different coloration of this area, which shows that this road maybe dammed up this area and caused a die-off of vegetation and changed the hydrology. So even though there have been human-induced changes to hydrology of wetlands, sometimes that cause degradation, the module briefly went into what you can do to help restore wetlands. You can restore the hydrologic function, you can create artificial wetlands, you can also manipulate the stage discharge relationship by lowering or raising culverts or outflow structures, and you can also change their shape and size. Another thing you can do is plug ditches. Over here on the right-hand side, I actually have a ditch plug that was installed at a mitigation site I monitor, and the ditch runs this way, and we are actually on the upstream side of it. So this water stain line is where the water normally sits. I just happen to be here on a dry period of the year. And as you can see, the water is hitting this ditch plug and stopping. And it helps to now dissipate and return the hydrologic flow to the adjacent wetlands instead of running quickly through the ditch. Another restoration approach you can use is to remove artificial obstructions or roads. The bottom picture is on another one of my mitigation sites, and this area used to have culverted crossings with an elevated road. We removed those culverts, lowered the road elevation, and allowed the water to free flow over it. The road is still used, and there's actually riprap gravel under here that allows trucks to go in and out even at high water stages. But it lets the hydrology return to more of a natural system. And with that, we reach the end of EPA's method for evaluating wetland hydrology. I hope you enjoyed the presentation. I apologize for the length, but the module is actually pretty long and detailed, and this was just an overview. To help give this overview, I sourced a lot of images from online as well as my personal endeavors, so I hope that helped bring the information across. Thank you.